A major goal of multivariable calculus is to extend concepts from single variable calculus into a higher dimensional case. And so we're going to begin to do that with the idea of vector-valued functions. A vector-valued function is a function whose output is actually 3 or more dimensional, and whose input, however, remains just one-dimensional. So in this case, I've got a vector-valued function r of t. The vector-valued function has a single input t, and that t is just some scalar. It's a real number. But its output has a x, y, and z component. It's an f of t in the I hat direction, a g of t in the j hat direction, and an h of t in the k hat direction. Here, the f, the g, and the h, those are what we call scalar functions, the kind of functions you would have seen back in single variable calculus, one input t and one output. But because I have 3 of them, all multiplying the 3 canonical unit vectors, then what I have is a 3-dimensional output. I'll give you an example of what these kind of things look like. Consider this particular case. So this is the vector value function, cos of t in the I hat, sine of t in the j hat, and just t in the k hat. Well, if I put up a 3-dimensional plot here, my x, y, z coordinate system, notice that I put on a pink dot. And what I mean this referred to is, what happens if I put in t equal to 0 into this equation? So I've got r of 0, cos of 0 is just 1, sine of 0 is 0, and just 0, of course, is 0. So what do I have? 1 in the I hat and nothing else. So this pink dot represents the point 1, 0, 0. That occurs when the input t is equal to 0. Well, now let me increase my values of t, and the computer's going to plot it, and it's going to look a little something like this. This is a helix. It's a spiral. And it sort of should make sense that it does, in fact, look like this. Consider the z component, the k hat direction. This is just multiplied by t. So as t gets larger, the z component gets bigger and bigger and bigger, which makes sense as my helix just rises. And if I consider the x and the y, well, if I do say, how about x squared plus y squared? So this is cos squared plus sine squared. By the Pythagorean identity, this is just equal to 1. This is the equation of a circle. Indeed, when you take that equation of a circle and you consider the third component, the z direction, what you really just get is a cylinder, and all of these points on this helix are constrained to live on that cylinder. So it makes a lot of sense that you'd have this kind of helical behavior. By the way, one example of these in nature is if you take an electron and you put it in the presence of a constant magnetic field, you can get helixes something like this. If I want to take an example that's a bit more interesting, well, look at this one. It's a different r of t. So a more complicated one that's a little harder to get intuitively, but it makes a sort of 4-leaf clover. And if I rotate the x and the y around, you can perhaps get some perspective of what this weird path looks like. So as you change what the r of t is going to be, you can get all sorts of really interesting things that may model all sorts of interesting behavior in the real world. All right, let's do some calculus on these vector-valued functions. Let's return to the helix. And what I want to try to do is describe a tangent vector. So I'll start at that pink t equal to 0 spot, the 1, 0, 0. And a tangent vector looks like this. It's telling me the direction where the curve appears to be going at that moment. It sort of tells the analog of what the slope was when we were talking about just graphs in 2 dimensions. Indeed, if I then allow my t to increase, my point goes around the helix, but so does the tangent vector, always pointing in the direction where my curve appears to be going. It goes around and around the circle, and it's always pointing just a little bit up because my helix is indeed increasing. So that's sort of visually what I'm hoping for in a tangent vector. This is indeed completely analogous to what we had in the case with just single variable functions, but how exactly do we define it? Now, I'm going to again work with the analogy of what we did with single variable functions. So my goal is to find a derivative. You'll recall that in single variable calculus, the slope of a curve was given by the derivative of the function. So I want to find the derivative of this vector r. So I want to find dr dt. I've zoomed in a little bit on my graph. I've got some particular point. I've got this tangent vector. That's what I want to go and compute. Now, how do I do that? Let me consider what I'll call this difference quotient. On the top, I want to have the difference between r at some point t plus delta t and some point r, and on the bottom, just the difference delta t. So if I have my 1 point, My r vector is just going to be the vector that goes from the origin out to my point. That's what I mean by r. Then r of t plus delta t is just some other point along the curve. It's what happens when I plug in t plus delta t, and I'm going to have some other vector, r of t plus delta t, going from the origin to that point as well. Now, let's consider the vector that goes between these 2 points. Well, this is the vector r of t plus delta t minus r of t. That is, that's just the numerator of my difference quotient. Okay, so that's the numerator. What about the entire difference quotient? So I have to take this vector and I divide it by delta t. Delta t is a scalar, so that does not change its direction. It's still pointing in the same direction as the yellow vector, but its length may change. For example, if this delta t is a very small number, less than 1, then dividing by a number less than 1 would make it larger. Perhaps it would look something like that. Okay. So that's a pretty good example of a difference quotient. We have this yellow vector that references our difference quotient, and completely analogous to what we did in single variable calculus. Okay, next step. Now let me make my delta t closer and closer to 0. That is, my 2 points, I want to make them closer and closer together. So if they start relatively far apart, I'll step in once, and twice, and 3 times, and 4 times, and I keep on making my 2 points closer and closer and closer together. And now what you'll see is that that yellow vector, the difference quotient, is getting closer and closer and closer to my goal, the tangent vector. So let's put this in a limit, and that will be our definition. Namely, we will define the derivative, dr dt, to be the limit as that delta t goes to 0 of the difference quotient, the r of t plus delta t minus r of t, all divided out by delta t. That is going to be my definition of the derivative of a vector valued function. All right, I'm going to step away for a moment because this is going to take a lot of space, but let's actually try to relate this to the original functions, the f of t, the g of t, and the h of t. That is, my r vector has these 3 different components, and I sort of want to split it up into the I hat, the j hat, and the k hat components. So the way I'm going to do that is first just look at the numerator, the difference quotient, the r of t plus delta t minus the r of t. And I notice that I'm going to subtract, well, what is r of t plus delta t? Well, it's the sum of all those 3 things, but with t plus delta t put in. Then I subtract off those 3 things, and this is what I get. Then I can rearrange a little bit. So I'm going to put all the stuff with f together, and that's going to form f of t plus delta t minus f of t, all of that in the I hat direction. Then I put the green g of t stuff together, that's in the j hat direction. And then I put the blue h of t stuff together, that's going in the k hat direction. So I've just rearranged some terms and put in some brackets, that's totally valid. All right, now what I want to do is go and look at the difference quotient with the limit out of the front of it. Okay, so what am I going to do when I take the limit as delta t goes to 0? Well, I can do this term by term. Indeed, if all of the individual limits exist, the limit of a sum is the sum of a bunch of limits. So first I have the limit as delta t goes to 0 of f of t plus delta t minus f of t divided by delta t. That's the one in the I hat direction. Then I have an analogous one in the j hat direction and an analogous one in the k hat direction. So basically I've just taken my limit definition and written it out, but breaking it up into the 3 different components. But now I should recognize these different things. That is, what is the first limit, the pink one? The limit is delta t goes to 0 of the f's. Well, that is nothing but what we've seen in first year calculus. This is all a single variable function. Remember, f is a scalar function. And so this is just df dt in the I hat direction, dg dt in the j hat direction, and finally dh dt in the k hat direction. So as long as my f, g, and h are differentiable, then I have my derivative split up in precisely this way. By the way, there's 2 different types of notation. This notation I've just written is Leibniz's notation. So this is dr dt is equal to df dt in the I hat, dg dt in the j hat, and dh dt in the k hat. However, if you prefer to use Lagrange's notation, that's the one with primes, you can do that just as well. And then you would say r prime of t is going to be equal to f prime of t in the I hat, g prime of t in the j hat, and h prime of t in the k hat. So the actual task of computing these derivatives is pretty straightforward. If I give you the f, g, and the h, you should be able to compute those and you just add them up.